Welcome to our Chapter 8 problem solving video. We're going to try something a little bit different here, going through the worked examples in the book rather than just the homework problems. If you guys like this better, we'll kind of transition to this style. If you guys don't like this better, we'll go back to the old style and I'll repeat another video for Chapter 8 just so you can have it in the style that you prefer. So we're going to start out with mole-to-mole conversions. Again, the biggest thing about Chapter 8 is balancing our equations, which was really from Chapter 7, but you can't do, stoichiometry without balanced chemical reactions. So we balance our chemical reactions. We can't convert from grams to grams. We can convert from grams to moles and moles to grams. So the, in-between step of going from grams to moles to grams is to go from moles to moles. So in this case, we're going to take sodium chloride, and we know that we have 3.4 moles of chlorine gas. We're going to make sodium chloride. We'll make 2 moles of sodium chloride for every 1 mole of chlorine gas, and every 1 mole of chlorine gas reacts with 2 moles of sodium metal. So we're just going to assume there's an excess of sodium. So this is not a limiting reagent equation. This is just you have one piece of given information, plug it in, and see what comes out at the very end. So we want to figure out what the moles of NaCl is. So given 3.4 moles of chlorine gas, we'll use our mole ratio, 2 moles of sodium chloride for every 1 mole of chlorine. So we're essentially just going to double the number of moles. So now we plug in our initial condition to our solution map or to our conversion, and we get moles of chlorine cancels out with moles of chlorine. We're left just with moles of NaCl, and we get 6.8 moles of sodium chloride. Pretty simple, pretty straightforward. We're just going to continue to build upon this, going from moles to grams to moles to grams to grams. So here's another example of the problem that you could take. So if we had some amount of O2 or H2, how much water would we have? So you could say, if I had 5 moles of O2, how much water would I make? Well, if I had 5 moles of O2, I'd make 10 moles of water. If I had 5 moles of H2, I'd make 5 moles of water because 2 to 2 is really just a 1 to 1 ratio, and 1 to 2 is just a 1 to 2 ratio, or twice as much as what you started with if you're talking about oxygen to water, or even oxygen to hydrogen. You need 1 equivalent of oxygen to 2 equivalents of hydrogen, 1 mole to 2 moles. You could plug in numbers for these and do a whole bunch of different problems. So if you want to see these type of problems in the book, some of these, are homework problems, some of them are not. So if you're just looking for extra practice, some of these example problems can be helpful. So if we had 24.6 moles of O2, how much H2O would we make? Well, remember, it's a 1 to 2 ratio, so we'd have twice as many. So 49.2 moles of water at the end. So now we're going to do mass to mass. This is the important one because, knowing how many moles you have is nice. It can be informative, but in the real world, I don't know what, a mole of some random compound actually looks like. I'd have to know what the density is. I'd have to have some practical application and experience with that chemical. However, grams, we know how much things weigh. And so grams is a much better intuitive measure of how much something is. So we're going to now go from grams to moles to moles, like we did in the last one, and then moles to grams. Again, grams to moles and moles to grams, we just use our molar mass, the sum of all the masses from the periodic table combined. So the mass of CO2 is 44, the mass of water is 18, the mass of oxygen is 32. Off the top of my head, I don't know what the mass of glucose is. It's 100 something. So we can figure out how many grams of CO2 is needed, or how much glucose can be produced from this amount of CO2. So first thing we want to do is convert our CO2 into moles, then moles of CO2 into moles of glucose, and then moles of glucose into mass of glucose using the molar mass of glucose. So this is our solution map. Now we want to figure out what our conversions for each step is. The molar mass of CO2, the mole ratio between CO2 and glucose and the molar mass of glucose. So we'll plug those ratios in, making sure that whatever unit on the bottom is going to cancel out with our unit on top. And so at the end, we'll just have our grams of glucose that won't be canceling out. Now we can plug in our starting value and calculate all of these intermediate values. Our starting value will be grams of CO2, and our finishing value will be grams of glucose. These intermediate calculations are just what we get when we convert from one thing to another thing. So we'll plug in our 58.5 grams. Our grams of CO2 will cancel out with the molar mass. This is the molar mass reciprocated. So remember, if we go from grams to moles, we divide by the molar mass or multiply by the reciprocal. If we're going from moles to grams, we multiply by the molar mass. So over here, we're multiplying by the molar mass, where here we're dividing by the molar mass or multiplying by the reciprocal of molar mass. So we get rid of our grams of CO2, we just have moles of CO2. We get rid of our moles of CO2 by doing the mole conversion. Then we do our molar mass for glucose to get the grams of glucose. So you want to make sure your units are correct. You want to make sure your reactions are balanced. All of these things are just things that you want to check after you've finished. Even during the process, it's always good to double check yourself. You don't want to be double checking yourself so much that you don't get anything done. That's why I say, in between major steps of the problem, like if you had, 3 reactions you're doing, maybe after each reaction, you'd want to check everything. In this case, we only have 1 reaction. I would balance the reaction, make sure it's balanced. Then I would do my mathematics or conversions like we just did, the stoichiometry. And then I would check my math. Here we have another example of a similar type of mass-to-mass conversion problem. Instead, we have magnesium hydroxide and hydrochloric acid reacting to make water and magnesium chloride. First thing you want to do is figure out what our given piece of information is. So we have 5.5 grams magnesium hydroxide, and we're going to want to figure out how many grams of HCl can be reacted against this. So this is kind of similar to what you might see on a challenge question for exam 2. I'll give you some amount of octane or some amount of oxygen. You'll have to complete that reaction with CO2 and water because that's what we get from the complete combustion of a hydrocarbon. We'll then figure out what the stoichiometry is and then relate how much octane or how much oxygen will react with how much of the other given one. So in this case, we convert grams to moles, moles of magnesium hydroxide to moles of HCl, and then moles of HCl to grams of HCl. Here are a couple practice problems like this. The next type of problem that's very similar to this is the limiting reactant problem. So we have a couple different terms that we're going to throw up in here. We have a theoretical yield. The theoretical yield is just what we're calculating on paper. The limiting reactant is when we have more than one given piece of information. So in here we have 2 pieces of given information, 0.552 moles of aluminum and 0.887 moles of chlorine. One of those is going to be more than the other. Now, you can't make more than what your least amount of reagent allows for. So if I only have a tiny, tiny amount of aluminum, but I have all of the chlorine in the world, well, it doesn't matter that I have all of the chlorine in the world. It only matters how much aluminum I have, because once I run out of aluminum, the chlorine doesn't have anything to interact with. It doesn't have anything to react with. So you can't make more aluminum chloride. So the limiting reactant, or the one that there's the least stoichiometric amount of, is the one that determines how much product you're going to make. So the book has a little bit different of a method for doing this than I would do it. The book method is totally correct. It'll give you the same answer that I get doing my method. However, the book's method is a little bit more work. So we'll go over the book's method because that's what's going to be presented to you when you're not interacting with me. So the book's method is to figure out how much product we're making from each given piece of material. So if we have this much aluminum, how much aluminum chloride do we make? If we have this much chlorine, how much aluminum chloride do we have? Whichever one makes the least amount of aluminum chloride is going to be your limiting reagent. Now, in order to do this, we have to figure out how much aluminum chloride we actually make, which is a couple extra steps. If they give us moles, it's not too much extra work because we're just going to multiply by the mole ratio to get are moles of product, and then whichever one has the least number of products is fine. So not much extra work there, but typically we start with grams because you can't measure moles. There's no real way to measure moles in the laboratory. You have to measure grams. So realistically, you have to go from grams to moles, and then moles to moles. Just divide by your mole ratios. So if we go back to here, we have a mole ratio, or our stoichiometric coefficients. We want to divide aluminum by 2 and chlorine by 3. Instead of dividing aluminum by 2 and then multiplying by 2, and dividing chlorine by 3 and then multiplying by 2, just take out that extra multiplication step and you have the answer. Whichever one has the lowest number is going to be the answer. It'll give you the same exact answer as what they do, just half the work. So not a big deal when you're starting from moles and you only have 2 things that you're comparing. But say you're starting from grams and you have 10 reactants. Do you want to solve 10 total reactions? Or do you just want to figure out what the mole equivalences are, everything? If you have to solve them for 10 extra reactions, that's 15, 20 extra multiplication and division problems you have to do, instead of just figuring out which one has the lowest equivalence. The equivalence is how many of this can react with how many of this, reacts with how many of this. So we would say that in this reaction, we'll go back to the reaction scheme. In this reaction, 1 equivalent of aluminum is 2 moles. 1 equivalent of chlorine is 3 moles. 1 equivalent of aluminum chloride is 2 moles. So we just divide by their stoichiometric leading coefficients, and that's how we figure out how many equivalents we have. So we can go back to this. We want to make sure that everything cancels out. Once we have our one with the lowest moles, that's just the answer. So again, I really, really disagree with the book's method of just solving for every single possible thing you can and then picking out the right answer at the end of the day. There's really no logic or intelligence in just plugging in every single number you can to get every single answer. As scientists, you want to do things in an educated manner. You don't want to just plug and chug through your entire life. You're going to end up wasting time. And so we want to be smart about how we do these things. And that's why I suggest not doing it the book's way. However, if you do it the book's way, you will get the right answer. You're just going to waste a lot of time. So again, we want to double check, do these things make sense? If I started with 5 grams, there's probably no way that I'm going to end up with 5 million grams. Likewise, if I start with 10 kilograms, it's unlikely that I'm going to end up with, 0.0001 kilogram. Just keep these things in reference, make sure that everything makes physical sense. We're doing things that are physically real. They have to make physical sense. So here would be another example of a problem. We could take sodium and fluorine as elements, react them to make sodium fluoride. There's a 2-to-1 ratio between sodium and fluorine, and then sodium fluoride has 2 moles for every 1 unit or 1 equivalent of reaction. So again, 1 equivalent of sodium would be 2 moles or 2 atoms, if you want to be really particular. 1 equivalent of fluorine would just be 1 molecule or 1 mole of fluorine gas. 1 equivalent of sodium fluoride would just be 2 molecules or 2 moles, depending on how you reference it. So again, the way that I would do this is I would take our moles, divide by our stoichiometric leading coefficients. So take 4.8, divide by 2, take 2.6, divide by 1, or just leave it as 2.6. 4.8 divided by 2 gives me 2.4. 2.4 moles is less than 2.6 moles, so sodium is my limiting reagent. I didn't have to do any product conversions to figure out which one was going to be my limiting reagent. And a lot of times, if it's a multiple choice question, it's going to ask you which one's your limiting reagent. So you can do a whole bunch of math and figure out which one's your limiting reagent, or you can do intelligent math and save yourself, half the time. So with this idea of limiting reactants, theoretical yields, we have a percent yield. We're not going to do this very often in the lecture or the exam parts of the class. This is almost exclusively going to be covered in the laboratory experiments, because a percent yield is relative to what's actually happening. You can't calculate what actually happens. You can make a theoretical approximation of what actually happens. And that's what we've been doing, is just doing theoretical yields, presenting things that happen in a perfect world. We don't live in a perfect world, so things always go awry. Whether it's a little bit of your product gets stuck to the container, or you spilled a little bit, or the reaction didn't go as long as it should have to go to completion. There are all these things that affect, the actual yield versus the theoretical yield. And so in reality, you're never going to get more than a 99% yield. The smaller your reaction, the lower your percent, or the lower your percent yield, or the lower your actual yield is. And actual yield is something that has to be observed or given to you. And that's why it's not very useful for the lecture portion of the class, but it will be important for the laboratory application of chemistry. So if we have 11.5 grams of copper and this many grams of copper oxide, and we produced this much copper, we could figure out what the theoretical yield was by just doing, a standard theoretical problem. Plug in our givens to figure out which one is our limiting reaction, determine what our final amount of product or theoretical yield is based on the limiting reactant. Then we take our observed mass divided by our theoretical mass to get our percent yield. A percentage is always just some part divided by the whole. In this case, the part is the actual yield, and the whole is the theoretical yield. So, again, just kind of saying the same thing that we said about figuring out what a limiting reactant is. Which one has the least amount of material? Again, they look at it as product. I would rather you look at it in terms of starting material, because that's just a more useful application of the technique. But again, we can solve for the grams of copper in both cases. Whichever one gives you a lower mass of copper is going to give you the limiting reagent. Again, if you just figure out the equivalences of the starting materials, that'll give you the same answer, but the book doesn't do it that way. So we would take 87.4 grams of copper and divide it by 101.7. Then you can multiply by 100% to put it into the percentage format, or you can just leave it in the decimal format. It's totally up to you. Obviously, calculations have to be done with a decimal. You can't do calculations with a percentage. So, obviously, if we did it with copper or carbon, we get a little bit more copper. If we do it with the copper oxide, we get less copper. So that has to be the limiting reagent. If we would have just divided by their molar mass, and then, it's a 1-to-1 chemical reaction, all we had to do is divide by their molar masses, and then whichever one was a smaller number was the one that we had to do. So we could have saved, 2 steps. So 1/3 of the total work could have been eliminated by just being a little bit more intelligent about how we look at this problem. So again, any percentage is just, the amount that we care about versus the total amount. In this case, the theoretical is the total. Sometimes your actual will be greater than your theoretical, and you can have greater than 100% yield. What that means is you contaminated your product. You either have extra solvent in there, you dropped something in there, you didn't weigh something out correctly. Somewhere along the way, you made a mistake. You can't have more than 100%. However, you can add stuff that isn't what you're actually looking for. So, just making sense, it should be less than 100%. Anything over 100% isn't necessarily incorrect. It just means that you made a mistake in the opposite direction. Like I said, percent yields over 100% mean that you contaminated it, you didn't completely dry the solvent, or, something happened that you didn't expect or you didn't account for. Maybe you measured something wrong. Maybe you weighed something out. Maybe you wrote the mass down wrong. Maybe it was 62 grams and you wrote 52 grams. That's a big mistake, and will cause a shift in your theoretical yield. So here's another problem. You could do this if we had 185 grams of iron 3 oxide and we had 95 grams of CO. How much iron metal could we produce? You plug these in. Again, you can either solve for the total amount of the problem, how much total iron do we make, or how much total CO2 do we make for each given reagent. But I would suggest, divide 185 by the molar mass of iron oxide, divide 95 by the molar mass of CO. The stoichiometric coefficient for iron oxide is just 1, so we don't need to do anything else. Stoichiometric coefficient for CO is 3, so we divide the moles of CO by 3. Whichever one gave you a smaller number would be your limiting reagent, saving you, a third to half of the work that you'd have to do to figure out the products of everything. So one thing that we introduced that was new in this class, essentially chapter 8, except for enthalpy, was the combination of chapter 6, moles and grams conversions, and chapter 7, balancing chemical reactions. You throw those together, and we have solving for quantities and chemical reactions. However, enthalpy is kind of it's absolutely a new concept. Enthalpy is just heat, but instead of using heat transfer like we did in the Q equals mc delta T equation, that's heat transfer of objects touching. Enthalpy is heat transfer due to chemical changes. So when we have a negative enthalpy, that's related to an exothermic reaction. When we have a positive enthalpy, that's related to an endothermic reaction. Exothermic gives off energy, endothermic takes in energy. That energy is absorbed or released in terms of the energy of the chemical bonds. So either the energy of the chemical bonds increases by however much energy was absorbed, or the energy of the chemical bonds is given off, typically in the form of heat, but it can also be work or other physical transformations. Delta H is also used for determining the energy from changing from a liquid to a solid, or from a solid to a liquid, or liquid to a gas to liquid. Those are all enthalpetic terms. So we have a combustion of a gas, propane here. This is a negative enthalpy, so this is going to be exothermic, which makes sense. We burn fuels so that they give off energy, so we should have a negative enthalpy here. If we have a given amount of grams of propane, we can convert to the moles of propane, and then these standard enthalpies, delta H, R, and X, is the kilojoules per mole of a reaction. So this is in relation to propane, so we'd figure out how many moles of propane we have, and then multiply these numbers. Since we have moles times kilojoules per mole just gives you kilojoules. So we have this many grams. We need to divide by the molar mass of propane, which is, carbon weighs 12, hydrogen weighs 1. So we have 44. So we'll have, 44.11 if you carry all the, averaged rounded decimals of the related masses, but 40 is pretty close. We'll do our mole conversion, making sure that grams cancels out. We'll get moles. And then, like we said, this is a standard enthalpy, kilojoules per mole of compound. So moles will cancel out, and we just get our kilojoules. Now we can plug in our starting amount of matter, 11.8 times 10 to the 4. This is not proper scientific notation, but nothing about this says that it has to be proper scientific notation. We're just putting it in a convenient notation. So after exam 1, which we're beyond, we don't really have to worry about scientific notation and sig figs until we get back to the final. If you'd like to consider scientific notation and sig figs for the entire class, you're more than welcome to. It might help you once we get to the exam, but not going to be required for receiving full points. So we want to make sure that all of our units cancel out, and then at the end of the day, we just get the desired unit we want. Make sure that this makes sense. If you're doing an exothermic reaction, you should have a negative value. If you're reacting more than 1 mole of material, you should have more energy than the standard enthalpy. Likewise, the opposite way, if you're doing an endothermic thing, should be positive. The amount of energy should make sense given what you're doing. So we have 155 grams of ammonia. That's way more than 1 mole. 1 mole weighs 17 grams. So we can guarantee that the delta H of this reaction is going to be way larger than 906, at least by close to an order of magnitude, because ammonia weighs 17 grams. Well, we almost have 10 times of what a mole is, so we should have almost 10 times of what this is. Just a real quick logical check. Here's another example, except for this is not a balanced equation. So the book did something that we're not allowed to do here. And I don't know why they would do this. It's just not proper. You want to have whole number ratios for your leading coefficients. So what we should have had was 2 moles of octane, or not octane, butane, 13 moles of oxygen, to 8 moles of CO2, to 10 moles of water. That's the proper way to do this. Again, I just left it how it's presented in the book so that, if you go to review this, you see the same thing. Again, the answers you get will be the same because, it's just however many moles of, CO2, and it's just based on this. So the previous problems, we were going from mass or matter to energy. Now we're given energy and we can go reverse. Remember, this is kilojoules total. If we divide kilojoules by the kilojoules per mole, we'll get moles. If we multiply moles by the molar mass, we get the mass of CO2 that we produced. Or really the mass of methane that we had, or butane, and then we can convert butane into the CO2. So here's kind of a highlight of the challenge question. Feel free to take a look at this. We've gone over the challenge question a little bit at this point in time, and we'll continue to go over it until the exam after spring break. And so this is actually a harder version of the challenge question. So they give you, about how much petroleum is burned every year. We're going to assume that the petroleum is just octane, and we want to calculate how much CO2 is produced per year. Now, once you do that using our balanced reaction, see here, they actually balanced the combustion of octane correctly. They didn't use, these half stoichiometric coefficients. You're not allowed to do that. You'll always have to multiply them up to the whole number ratio. Instead of having 12.5 here, we rounded it up to 25, 2, 16, and 8 instead of 1, 12.5, 8, and 9. Always have to have whole number ratios for your stoichiometry. Once we've balanced this and figured out how much CO2 is produced every year, we can take the amount of CO2 in the atmosphere and figure out how long it's going to take to double the total amount of CO2 in the atmosphere. If you have any questions about this or another variation of this problem, please make sure to reach out via email or office hours. Otherwise, I'll see you in lab or after spring break.